looking at the 3739 review, along with graphing, your first three questions are optimization questions. Those come from 3.7. That's where you're trying to maximize something or minimize something using a separate equation. So number one says you want a point on the curve of 2y equals x squared that is nearest to 4, 1. So if I'm looking for something that is close to something nearest, this is minimum distance, which means I'm going to need to derive distance. So I need to know the distance formula. It is the square root of x minus x squared plus y minus y squared, being points, the whole x1, y1 thing, it doesn't really matter. I have a point for 1, plug it in. I'm going to put it in for the second one. X minus 4 squared plus y minus 1 squared, and this is essentially what I want to derive. I can't derive just yet because I still have x and y. So that's where this equation comes into place. Solve it for a letter. I'm going to solve it for y. That is my easier one to solve for. So divide by 2. Y equals x squared over 2, or 1/2 x squared. So now I'm going to plug it into my distance formula. So distance will equal square root of x minus 4 squared plus 1/2 x squared minus 1 squared. This is what I want to minimize. This is what I need to derive. As long as everything under the radical is minimized, my radical is minimized because the square root is just a basic function. As long as the number underneath is as small as possible, everything is as small as possible. So I'm going to derive x minus 4 squared plus 1/2 x squared minus 1 squared. This is what I'm going to derive. So d prime will be, and this is going to be chain rule. Take the 2 to the front. So we'll have 2 x minus 4 drops to a 1 power. My derivative of my inside is just 1, plus, bring the 2 to the front, 2, 1/2 x squared minus 1 to the first power, and the derivative of the inside would be 2 times 1/2, so that's just 1x. Now I'm going to derive inside equal to 0, so I have 0 equals 2 times x minus 4. I don't need to do anything with the exponent or the times 1. And then I have 2 times 1/2 times x. So I'm going to distribute that 2. So I have 2 times 1/2 x squared would just be x squared. And 2 times negative 1 is negative 2. And this is going to be times x. I haven't done anything with that x yet. That comes after. So I have 0 equals 2 times x, 2x, 2 times negative 4, negative 8, x squared times x, x cubed, and negative 2 times x, negative 2x. Just combine my like terms now and solve. So I have 2x minus 2x, that goes away, and I have x cubed minus 8. Add 8 to both sides. 8 equals x cubed, so then x is 2. Now the question specifically asks for, and the point on the curve, so I would need to plug in and find out what the y value is. 2 times y equals x, which is 2 squared, so 2y equals 4, so y is 2. My coordinate is 2, 2. This is letter option B. Number 1, distance formula, nearest, minimum distance. Next, personally I think that number 2 is the hardest one on here. It says, a company wishes to manufacture a box with a volume of 40 cubic feet that is open on top and is twice as long as it is wide. So my length equals 2 of my W. Find the box that can be produced by using the least amount of material. So that's like wrapping paper. Surface area. I'm going to draw this box. It does not tell me if it's a square, so I cannot assume that. I just know it's a rectangular box. So I have the bottom is a rectangle, up, up, across the top, and then, sure. Not really sure what angle this box is coming out at, but it doesn't matter. I know its volume is 40, and you have width and 2 width for the length. So volume is length times width times height. And surface area is area of the bottom. So this whole bottom, that has an area of base times height. So width times 2 width, 2w squared. It is open top, so I don't have to do anything about it. And then look at its sides. I have this side and this side that are the same. This dimension is height. So I have 2WH, so plus 2WH. And then I have this side and this side that are the same. So I have 2 of those. Move this box out of my way. So I have 2 of those, so I have plus 2. And its dimension is 2W times H. So my surface area is 2W squared plus 2WH plus 4WH, or 2W squared plus 6WH. This is what I'm trying to minimize, so this is what I'm going to need to derive, which means I need to use my volume to help me solve for either W or H. Right now I can't derive with 2 different variables. So what I know over here with volume, I know my volume is 40. I know my length is 2W. I know my width is W. My height is H. So 40 equals 2W squared H. Okay, I can solve for a letter. I'm going to solve for H. 2W squared. Divide by that. So 20 over W squared is my height. Take that height, plug it in right here, and my surface area will be all in one variable. I'll be able to derive it. So surface area equals 2W squared plus 6W times H, which is 20 over W squared. So I have surface area equals 2W squared plus 120, and W over W squared will land me with 1W. Rewriting it one more time so that I don't have any fractions. This would be 120W to the negative first. Okay, so I have just completed my surface area equation. I needed to use the volume in order to get that. Now I can start the calculus. So far we've just pretty much done a system of equations, plugging one into the other. We haven't done the calculus part yet, which would be to minimize, use the least amount of material possible. So this is what I'm going to want to minimize, so that's what I'm going to need to derive. Okay. So let's go ahead and derive it. So, surface area derived, SA prime. This is going to be a 4W, no power, just power of 1, minus 120 W to the negative second. Derive it, set it equal to 0. 0 equals 4W minus, this is 120 over W squared. Solve for W. I'm going to add the 120 over W squared. So I have 120 over W squared equals 4W. I need to get that W squared out of the denominator, so multiply by it. 120 equals 4w cubed. Divide by the 4. W cubed equals 30. 30 is not a perfect cube. That's okay. You can give me a decimal. Cube root. Cube root. W is, turn to your calculator. Press the math button, go down to cube root of 30, 3.1. The question says find the width of the box. Oh, that's all I have to do. Find the width of the box that can be produced by using the least amount of material, 3.1. I think this hands down was the hardest problem on the assignment. It just is the most involved and you had to know the most. Volume of anything rectangular, I would not give you. Volume of like a sphere or a cone or a cylinder, I would give you those. But a rectangle, y'all know how to find that kind of stuff. Number 3. If I have this, 3x plus y equals 12, what is the minimum value of the product xy? So this is what I want to minimize, so this is what I need to derive. Okay, so I'm going to want to derive that xy, which means I need to figure out something to plug in for either x or y if I'm going to derive it. So that's where this equation comes into play. Solve for a letter. And plug it in here. So I'm going to solve for y. That is the easier one to solve for. I'm going to subtract 3x from both sides. Y equals negative 3x plus 12. Take that y, put it right here. That is what I want to minimize. I want to minimize, and I didn't name it for you, so I'm just going to put minimum equals x times y, which is negative 3x plus 12. But you can call the function whatever you want. I just like to have an equal sign. So this is negative 3x squared plus 12x. This is what I want to minimize. In order to minimize, I need to derive and set equal to 0. So I would have 0 equals 2 times negative 3, negative 6x. And then this is a 1. 1 times 12. 12, the x will drop off. Solve for x. Add 6x to both sides. 6x equals 12. X equals 2. The question wants to know what is the minimum value of the product. So that means I need to find y, and I need to multiply them together to find the product. 3x, x is 2, plus y equals 12. That was my original equation. So 6 plus y equals 12. Y is 6. Their product is then 6 times 2, which is 12. Okay, number 4. Number 4, it gives you a graph. The graph 1, 2, 3, 1, 2 looks like this. Kind of like this. This is f prime of x. So this is the derivative. Okay, so it wants to know which can be true, which must be true. Statement 1. Relative minimum at x equals negative 3. Statement 2. F has point of inflection at x equals negative 2. And statement 3, concave down for 0 to 4. So, relating our first derivative to these things. Your first derivative tells you where extrema can occur. It also tells you when your original function was increasing or decreasing, and it tells you where points of inflection are. if you have a relative minimum at x equals 3, that means your first derivative changes from negative to positive there. So at x equals negative 3, here's x equals negative 3. I go from a negative number to a positive number. Yes, I have a relative minimum. If f has a point of inflection at x equals negative 2, well, looking at my first derivative, the way the first derivative is related to the second derivative is by deriving once. So when I have my second derivative equal to 0, that would be point of inflection. It is actually you only had to derive first derivative once. And set it equal to 0, which means the points of inflection are the extrema of the first derivative. So if I have a point of inflection at x equals negative 2, I would have a max or a min at x equals negative 2 of my first derivative. Well, here is x equals negative 2. It is not a minimum or a maximum. I was increasing and continue to increase. It is not a extrema, not that one. Okay, on that same token, concavity, if I'm concave down, that means my second derivative is negative. Concave down would imply second derivative of x is negative, which means first derivative of x is decreasing. Remember that the second derivative graph is the sign, positive or negative, is represented by the slope of my first derivative. The slope of my first derivative is the second derivative. So when my first derivative is decreasing, my second derivative is negative. So that happens all this time. My second derivative, or my first derivative is decreasing, which means I would be concave down from 0 to 4. Yes, so it'd be 1 and 3 only. That would be E. Number 5. I have a graph that looks like this. Okay, this is what it looks like. Again, this is f prime of x. It says the graph of f prime, the derivative of f is shown. F has a local max at x equals what? So a maximum is going to happen when my first derivative goes from positive to negative, increase or decrease. So I switch from a positive number to a negative number right here at x equals 1. See. So you're always comparing what it is that you were given and what graph are you relating it to. Next. 6. I give you this graph. At 3, I cross through. Kind of like that. That's good enough. Similar. A particle moves along that straight line. The graph of the particle's position x of t at time t is shown above for 0 to 6. So this is x of t, which is position. So that's my original function. The graph has horizontal tangents at t equals 1. So I was way off. I should redraw this curve. T equals 1. Point of and t equals 5, and a point of inflection at t equals 2. Let me just keep drawing this horribly. So all that means is that this has a horizontal tangent here at 1, horizontal tangent here at 5, and at 2 is my point of inflection. for what values of t is the velocity increasing? This means that velocity is changing. Spelled changing wrong. Which means derivative of velocity, which is acceleration, which is the second derivative. So I know that my second derivative is positive. So that means concave up. Tons of connections having to be made here. So this is really just asking for where is x of t concave up, which is why they gave you that point of inflection. You are concave up between 0 and 2. Up like a cup, down like a frown. So A. So you had to be able to relate the fact that velocity, first of all, is your first derivative. And if I want to change velocity, that means I had a derivative of velocity. The change in velocity is acceleration. And my acceleration is my second derivative, which on a graph is represented by concavity. So if my velocity is increasing, my second derivative is positive, which means I was concave up. Really how to make those connections there. Okay, number 7. Linearization. This means tangent line. I have x equals 4 and f of x equals 1 over x. If I'm writing the equation of the tangent line, I need x, I need y, I need m. So here I know x is 4, y is 1 over 4. I don't know why I wrote x is x. X is 4, y is 1 over 4, and m is f prime plugging in 4. So I'm going to need to derive this. I'm going to rewrite this as x to the negative first. So when I derive, I get negative x to the negative second, or negative 1 over x squared. So when I plug in 4, negative 1 over 4 squared is negative 1 over 16. The negative is not squared, the 4 is squared. So now when I write the equation of a tangent line, y minus y1 equals m, negative 116, x minus x1, x minus 4. Linearization. Write the equation of the tangent line. Number 8. Find dy. I give you that y is 5x minus 1 to the 3/2 power. I give you that x is 2. And delta x is 4. Okay, first of all, remember delta x is the same thing as dx. This here, in order to derive this, I'm going to need to do chain rule. So when I derive 5x minus 1 to the 3/2 power, I'm going to derive this whole thing. I get dy dx equals, bring my 3/2 to the front, 5x minus 1. My 3/2 gets lessened by 1, so I have 1/2. Now derive the inside, times 5. Okay, now I want dy alone, so I'm going to multiply by dx. dy equals 3 over 2 times 5x minus 1 to the 1/2 times 5 times dx. I'm going to plug these numbers in. I know x is 2, I know dx is 4. So dy equals 3/2 times 5 times 2 minus 1 to the 1/2 times 5 times 4. dy equals 3/2. This is 10 minus 1, that's 9 to the 1/2 power times 5 times 4. 9 to the 1/2 power is square root of 9. So I have 3 over 2 times 3 times 5 times 4. 2 is going to go into the 4 twice. dy will be 3 times 3, which is 9, times 5 is 45, times 2, 90. All right. Next. Number 9. Let f be a differentiable function so that f of 5 is 3, f prime of 5 is 2. If the tangent line to the graph of f at x equals 3 is used to find an approximation of a 0 or to a 0 of f, so 0 of f, what is that approximation? So that means that eventually, if f is 0, I have y equals 0. So what I know here from this information is that x is 5, y is 3, and my slope is 2. Slope at 5 is 2. So if I want to write the equation of the tangent line, y minus y1, y minus 3 equals m2 times x minus x1. Now find x when my function is 0, y is 0. So 0 minus 3 equals 2 times x minus 5. Negative 3 equals 2x minus 10. I'm going to add the 10. Negative 3 plus 10 is 7 equals 2x. Divided by 2. X is 7 over 2. Well, that sucks because f prime of x is negative 2. So I'm about to erase this whole thing. At least I caught it. Same exact process, different number. So my tangent line approximation is going to be y minus 3 equals m negative 2 times x minus 5. Distribute, y minus 3 equals negative 2x plus 10. Plug in 0. Minus 3 equals negative 2x plus 10. Subtract the 10. Negative 13 equals negative 2x. Divide by negative 2. X is 13 over 2. Cool. Number 9. Number 10. The figure above shows the graph of f prime, the derivative of f from negative 6 to 8. What describes f on the same interval? So to draw this one, sure. Wants to know, it looks like how many minimums, maximums, and points of inflection if you're looking at your answers. Minimum, maximum, point of inflection according to my first derivative. So a minimum is going to happen when my first derivative goes from negative to positive. A maximum is going to happen when my first derivative goes from positive to negative. And a point of inflection is going to happen when my first derivative has a max or a min. So first of all, I can figure out how many maximums and minimums I'm going to have for my original by how I change. This goes from a positive to a negative. This is a max. This one does not actually cross through. It stays negative the whole time, so there's not an extrema. And then you have one here. This is from negative to positive, so that would be a minimum. So I'm looking for an answer that has one max 1 min. And as far as points of inflection go, that would be any maximum or minimum that occurs on f prime. So here would be a point of inflection, here would be a point of inflection, and here would be a point of inflection. This little curvy thing over here is not actually a point of inflection because you don't change slope. You're decreasing the whole time. And extrema happens when you go from increasing to decreasing, when you have that change. So since that one doesn't actually change, no maximum or minimum happens there, which means no point of inflection for my second derivative. So I have 3 points of inflection. So 1 max, 1 min, 3 points of inflection, that's A. Number 11. The polynomial function has selected values of its second derivative f prime given in the table above. Which must be true. So 0, 1, 2, 3, 5, 0, -7, 4. Okay, so what has to be true? We've got A, B, C, D, E. F is increasing from 0 to 2. F is decreasing from 0 to 2, has a maximum at x equals 1, has a point of inflection at x equals 1, or changes concavity between 0 to 2. So, first of all, your second derivative tells you nothing about what the function was doing, increasing, decreasing, maximum. The only thing the second derivative tells you is concavity. You can find out where your first derivative changed due to the maximums and minimums of your second derivative, or your zeros of your second derivative, but it's still really, you don't really go backwards from second derivative. Second derivative only tells you concavity. So right away, we knew nothing if it was increasing, decreasing, or had a maximum. I can only look at point of inflection or concavity. Technically, your point of inflection would happen when your second derivative is equal to 0, but that's just possible points of inflection. You could have easily not crossed through the x-axis at that 0 and not had an inflection change. So let me graph that for you and show you what it would look like. If I had x equals 0, y equals 5, x equals 1, y equals 0, and x equals 2, y equals -7, I could have easily been up here at 0, 5, down here at 1, 0, and down here at 2, 7, 2, -7, and not crossed through my x-axis there. I could have done it there. So it's not necessarily a point of inflection. This one would not be a point of inflection because I don't actually cross through 0. I stay concave up that whole time. It just probably has that little shift like it had in the last graph where it just looks like a change, but it's not actually a change. So you can't assume that either. The only thing we can assume is that no matter what, going from 0 to 2, I had to have changed concavity because I had to have gone from a positive number to a negative number. So you can't assume that just because those numbers are given to us on the graph, that's the only thing that are on the table, that's the only thing that happened. That's why I always tell you guys to draw pictures and draw out the graph. It's so much easier. All right, number 12. Let y equals f of x to find a twice differentiable function. Let y of equals t of x be the tangent line. At x equals 2. If t of x is always greater than or equal to f of x, what has to be true? So I've got A, f of 2 is greater than or equal to 0. B, f prime of 2 is greater than or equal to 0. C, f prime of 2 is less than or equal to 0. D, f double prime of 2 is greater than or equal to 0. And E, f double prime of 2 is less than or equal to 0. So if my tangent line is greater than my original function at all times, that means my tangent line is above it. So if I draw a tangent line, maybe one that goes this way, my curve was underneath it somewhere. I don't necessarily have to finish it like that, but my curve was underneath it somewhere. Even if my tangent line went the other way, my curve is still underneath it because my tangent line always has a bigger y value than my curve. So that's what that means. So this pretty much only tells us stuff about concavity. I don't know that my y value for A, that y is greater than or equal to 0. This could have easily been in the negative portion of a graph. So you don't know that. You can't assume that. This would mean f prime of 2 is greater than or equal to 0, always increasing. Well, here is a decreasing, so it's not that. The next one, f prime of 2 is always less than or equal to 0. Well, here it is increasing, so it's not there either. The next one, f prime of 2 is greater than or equal to 0. That would mean concave up. Well, these are both concave down. So it is E, concave down. When your tangent line is above the curve, always your curve has to be below it. Your curve had to be concave down. 13. Evaluate dy. dy equals question mark. When y equals 6 over x plus 2 cube root of x, that's it. I give you x equals 8 and delta x equals 2. So delta x again means dx. And this is actually 6x squared. Okay, so I'm looking for dy, which means I need to derive this. Before I derive this, I'm going to rewrite it. 6x to the negative second plus 2x to the 1/3. This is what I'm going to derive. Y dy dx equals, this will be negative 12. Drop 1 to the negative third. 1/3 times 2 is 2/3 x to the negative 2/3. Now I'm going to be able to plug some stuff in. First, I'm going to try to get dy by itself, so move dx to the other side. dy equals negative 12 x to the negative third plus 2/3 x to the negative 2/3 times dx. I put that in parentheses because it has a plus sign. I didn't mean to do it twice. Because it has a plus sign, and all of it is getting multiplied by dx. So now I'm going to substitute in. dy equals negative 12 times 8 to the negative third plus 2/3 times 8 to the negative 2/3 times dx, which is 2. So I'm going to move these exponents around. This is negative 12 times 1 over 8 cubed plus 2/3 times 1 over the cube root of 8 squared times 2. And now I can simplify. 8 cubed. I don't know that off the top of my head. Hang tight. 8 cubed is 512. So this is negative 12 over 512, and then plus 2/3 times the cube root of 8 squared. You could cube root 8 and then square it, or square 8 and then cube root it. Cube root of 8 is 2, 2 squared is 4, so over 1/4 times 2. If I distribute this 2, then I have negative 12 over 256, and then this becomes a 1, this becomes a 2, plus 2 over 6. Now I can make them the same. Oh, dang it, this is going to be an ugly fraction. So, let's see, common denominator. I have no idea. Did I do something wrong? No. we're just going to use a decimal because that's going to be so much easier. I've got negative 12 divided by 256 plus 2 divided by 6 is 0.619. Happy with that. You could use your fraction button. It would be 119 over 192. I don't really care. And number 14 is the FRQ. Let f be a function divided on the closed interval from negative 3 to 4, with f of 0 equals 3. And f prime, the derivative, consists of one line segment and one semicircle, shown above. Here's the graph. It's got this point, negative 3, 1, and then it's really close together. This is a point, this is a point, this is a point. So this goes like this, and then like that. For lack of better arch skills, this is what it looks like. So, part A says, and this is again f prime, says on what intervals, if any, is f increasing? Well, that would mean that my first derivative of x is positive. So that happens from negative 3 to negative 2. So from negative 3 until negative 2, or you could say from negative 3 is less than or equal to x less than or equal to 2, would be equal, or increasing. And this is because f prime of x is greater than 0. It's a positive number. Part B. Find the x-coordinate of each point of inflection. A point of inflection comes from first derivatives, maximum or minimum values. So I've got a minimum down here at negative 2, 0, negative 2, and here at 2, 0. So the x-coordinates would be x equals 0 and x equals 2. This is where you can see a few different things. This is where, not these. F prime of x has extrema. You could say something like, this is where f prime of x changes slope. That also would be considered where you change from increase to decrease, anything like that, like f prime changes from increasing to decreasing. So that is where your point of inflections take place at. And part C. 1 second. There we go. Part C. Find an equation to the line tangent. So my tangent line, I need x, I need y, I need m. Tangent to the point, to the graph of f at 0, 3. So x is 0, y is 3. The slope, I'm going to find from the graph. M is f prime of x. So look at the graph at the x value of 0. When x is 0, my slope is negative 2. So my tangent line, y minus 3 equals m, negative 2 times x minus 0. You can leave it like that. You could distribute y minus 3 equals negative 2x plus 0. Or you could even write it in slope-intercept form. Boom. That is your 3739 with graphing review.